Welcome. Today, we embark on a fascinating journey into the world of artificial intelligence, the technology that is reshaping our world and redefining what it means to think, learn, and create. Before we begin, if you find this exploration intriguing, please like and share so more minds can awaken to the marvels of AI. Let's dive into the essence of how artificial intelligence works, explained simply yet deeply, revealing the mysteries behind machines that can learn, reason, and even imagine. Artificial intelligence, or AI, is often seen as a complex, almost magical force driving futuristic technologies. Yet at its core, AI is a creation of human ingenuity, a powerful system designed to mimic certain aspects of human thought processes. To understand AI, we must first understand that it is not a single thing, but a vast field encompassing many approaches and technologies, all aiming to enable machines to perform tasks that, until recently, only humans could do. Imagine a child learning to recognize objects. At first, the child sees countless shapes and colors without understanding what they mean. Over time, with guidance and experience, the child learns to associate certain patterns with names and meanings: a red ball, a barking dog, the warmth of sunlight. AI systems, in a simplified sense, do something very similar. They process vast amounts of data, identify patterns, and make decisions or predictions based on what they have learned. At the heart of many AI systems lies the concept of algorithms, step-by-step instructions a machine follows to solve problems or complete tasks. These algorithms are crafted by humans but gain power when combined with data and computational ability. Through these, AI can analyze images, understand speech, translate languages, play games, drive cars, and much more. One of the most important branches of AI is machine learning. Unlike traditional computer programs that follow explicit instructions, machine learning systems learn from data. Think of it as teaching a computer by example rather than by rules. Instead of telling the machine exactly how to recognize a cat, we provide it with thousands of pictures labeled cat and not cat. The system then discovers its own rules and patterns to distinguish cats from other objects. This learning process is inspired by the human brain's ability to recognize and categorize information, but AI does it through mathematical models. These models use statistics and probability to find relationships and make predictions. The better the data and the algorithms, the smarter the AI becomes. Deep learning, a subset of machine learning, takes this a step further. It uses structures, called artificial neural networks, designed loosely to imitate the neural connections in our brains. These networks have layers of interconnected nodes, or neurons, that process information in ways that allow the AI to tackle highly complex tasks, such as recognizing faces in photos, understanding natural language, or even generating creative content. But how does AI understand or think when it's just numbers and code? The key lies in how information flows and transforms through these layers. Each neuron receives input, processes it with certain weights, and passes the result forward. Through repeated training, the network adjusts these weights to minimize errors and improve accuracy. This process, called training, is the foundation of AI's learning ability. Yet AI is not just about mimicking intelligence. It also involves decision-making, problem-solving, and adapting to new situations. Reinforcement learning, another AI approach, teaches machines to make decisions by rewarding desired outcomes and discouraging mistakes. Like training a pet, the AI explores actions, learns from feedback, and gradually masters tasks such as playing chess or controlling a robot. Behind the scenes, vast computational power is essential for AI. Training deep neural networks requires processing massive data sets, often on specialized hardware like GPUs or TPUs, capable of performing thousands of calculations simultaneously. This intense computation allows AI to find subtle patterns and correlations invisible to human eyes. Data is the lifeblood of AI. The quality, quantity, and diversity of data determine how well an AI system can learn and generalize. With more diverse and representative data, AI becomes more robust, fairer, and more capable of understanding the complexities of the real world. Conversely, biased or insufficient data can lead AI to flawed conclusions or unfair outcomes. The applications of AI are vast and growing rapidly, from virtual assistants understanding spoken commands to autonomous vehicles navigating busy streets. AI is embedded in everyday technology. It powers recommendation systems suggesting what to watch or buy, helps doctors diagnose diseases, and enables artists to create novel works of art. However, this transformative power comes with challenges. Ethical concerns about privacy, bias, and accountability arise as AI systems influence decisions affecting millions of lives. The quest to build transparent, explainable, and trustworthy AI continues alongside the quest for smarter machines. In essence, artificial intelligence works by combining human-designed algorithms, massive data, and powerful computational models to mimic aspects of human cognition. Through learning, adaptation, and pattern recognition, AI systems gradually evolve from simple programmed instructions to sophisticated tools that augment human capabilities. This exploration of AI's inner workings invites us to reflect on intelligence itself, what it means to learn, to decide, and to create. As we venture deeper into this realm, we uncover not just how machines think, but how understanding intelligence illuminates our own minds. As we continue our journey into the heart of artificial intelligence, it becomes clear that AI's power lies not only in how it learns, but also in the kinds of problems it can solve. Understanding the different types of AI and their capabilities helps illuminate the many ways AI touches our lives, from simple automation to complex decision-making. At the most basic level, AI systems can be divided into narrow AI and general AI. Narrow AI, also known as weak AI, is designed to perform specific tasks. These systems excel in defined environments, like recognizing speech, translating languages, or recommending movies, but they do not possess consciousness or understanding beyond their programming. Today's AI applications, such as virtual assistants and image recognition tools, mostly fall under this category. In contrast, general AI or strong AI refers to machines with the ability to understand, learn, and apply intelligence across a broad range of tasks, much like a human being. General AI remains a theoretical concept, a horizon that inspires researchers but has yet to be realized. The pursuit of general AI involves immense challenges in replicating human cognitive flexibility, creativity, and emotional understanding. To appreciate how AI systems work on a practical level, it helps to examine the core processes involved. These generally include data collection, data processing, model training, evaluation, and deployment. Each step is essential to building AI that is effective, accurate, and reliable. Data collection is the foundation. AI systems need large volumes of data to recognize patterns and learn from examples. This data can take many forms: images, text, audio, sensor readings, depending on the application. For instance, a self-driving car gathers camera images, radar signals, and GPS data, while a chatbot learns from conversations and written text. Once collected, data must be cleaned and processed. Real-world data is often messy, inconsistent, or incomplete. AI practitioners spend significant effort preparing data, removing errors, filling missing values, and formatting it in ways the AI models can understand. This step, known as data pre-processing, is crucial because garbage in leads to garbage out. The quality of data directly impacts the AI's performance. After preparing data, the AI model is trained. Training involves feeding data into algorithms that adjust internal parameters to minimize errors in predictions or classifications. This process requires multiple iterations, allowing the AI to gradually improve its understanding. The model learns to associate inputs with correct outputs, much like a student practicing problems to master a subject. Evaluation follows training to test how well the AI performs on new, unseen data. This step ensures the model has not simply memorized the training data, but can generalize its knowledge to real-world situations. Metrics such as accuracy, precision, recall, and F1 score measure different aspects of performance, helping researchers select and refine models. Once validated, the AI system is deployed in real environments where it interacts with users, processes live data, and makes decisions. Deployment brings its own challenges, such as ensuring the AI operates efficiently, handles unexpected inputs gracefully, and respects ethical guidelines. Delving deeper into AI techniques reveals fascinating methods by which machines acquire and apply knowledge. One common approach is supervised learning, where the AI learns from labeled examples. For instance, a model trained to detect spam emails receives messages marked as spam or not spam, learning features that distinguish the two. Supervised learning is powerful, but depends heavily on the availability of labeled data, which can be expensive and time-consuming to create. Unsupervised learning, on the other hand, works without labeled data. Instead, it identifies patterns or groupings in raw data, like clustering customers by purchasing behavior or detecting anomalies in network traffic. Unsupervised learning allows AI to discover hidden structures and relationships, often revealing insights humans might overlook. A third type, semi-supervised learning, combines the two, leveraging a small amount of labeled data alongside a large pool of unlabeled data. This approach balances accuracy and data efficiency, making it useful in domains where labeling is costly. Another compelling technique is reinforcement learning, where AI learns through trial and error by interacting with an environment. It receives rewards for good actions and penalties for bad ones, gradually developing strategies to maximize success. Reinforcement learning has led to remarkable achievements, such as mastering complex games like Go and controlling robotic systems. Artificial neural networks, especially deep networks with many layers, have revolutionized AI in recent years. These networks can model intricate nonlinear relationships, enabling breakthroughs in image and speech recognition, natural language processing, and even art generation. Each layer extracts progressively abstract features from the input data, the edges in the first layer, shapes in the next, and complex objects deeper down, allowing the AI to build rich internal representations. Natural language processing, NLP, is a particularly exciting field, where AI interprets and generates human language. Using models trained on vast corpora of text, AI can translate languages, answer questions, summarize documents, and engage in conversations. Techniques like transformers have significantly advanced NLP, enabling machines to capture context and nuance in ways previously thought impossible. While AI's capabilities are impressive, it is important to recognize its limitations. AI models learn from past data and patterns, meaning they can struggle with novel situations or concepts outside their training. They lack true understanding, emotions, and consciousness. Their intelligence is statistical rather than experiential. Moreover, AI systems can inherit biases present in their training data, leading to unfair or discriminatory outcomes. Addressing these ethical issues requires careful data curation, transparency, and ongoing monitoring. The field of AI ethics seeks to ensure that AI technologies benefit society equitably and responsibly. In parallel, research continues into explainable AI, techniques that help humans understand and trust AI decisions. Since many AI models operate as black boxes, providing little insight into their reasoning, explainability is crucial for critical applications like healthcare, finance, and law enforcement. The future of AI holds tremendous promise and profound questions. As machines grow more capable, how will they reshape work, creativity, and human relationships? How will we balance innovation with privacy and fairness? These questions remind us that AI is not merely a technological challenge, but a societal one, requiring collaboration between scientists, policymakers, and citizens. Ultimately, understanding how AI works invites us to reflect on intelligence itself, its nature, its potential, and its limits. It challenges us to rethink what it means to know, to learn, and to create in an era where human and machine intelligence intertwine. To truly grasp how artificial intelligence operates, it is essential to explore the fundamental building blocks of AI: data and models. These twin pillars form the foundation upon which AI systems are built, shaping their abilities and limitations. The relationship between data and models is symbiotic. Data fuels models with knowledge, while models transform data into actionable intelligence. Data in AI is far more than just numbers or text. It represents real-world information, images of faces, recordings of speech, patterns of behavior, sensor measurements, and more. Every byte of data carries meaning, and how AI interprets this meaning depends on the models that process it. The richness, variety, and quality of data influence the depth and breadth of AI's understanding. For example, consider the task of teaching an AI to recognize handwritten digits. To do this, researchers use a dataset containing thousands of handwritten numbers labeled from 0 to 9. This dataset, known as MNIST, serves as a playground for experimenting with various AI techniques. The AI analyzes thousands of examples, learning to discern subtle differences in handwriting styles and shapes. The model, in this case, is typically a neural network designed to map pixel values from images to corresponding digit labels. During training, the model iteratively adjusts its internal parameters, called weights and biases, to reduce errors in prediction. These adjustments follow mathematical rules, guided by optimization algorithms such as gradient descent. The magic lies in how these models learn complex patterns. Unlike rigid programming, where explicit instructions are coded for every possible scenario, AI models discover underlying structures autonomously. They identify correlations between input features and output targets, developing an internal representation that captures essential characteristics. However, this process requires more than just raw data. The way data is prepared, cleaned, and organized is vital. Imagine if the dataset contained mislabeled images or blurry photos. The model would struggle to learn accurate distinctions. Data. Pre-processing techniques, such as normalization, augmentation, and filtering, enhance the dataset, making learning more effective. Another aspect of AI models is their architecture, the design and arrangement of layers and nodes that determine how information flows and is processed. Simple models might have only a few layers, while advanced deep learning models consist of dozens or hundreds, each specializing in extracting specific features. Convolutional neural networks, CNNs, for instance, have revolutionized image recognition by mimicking how visual information is processed in biological systems. CNNs use specialized layers that focus on detecting edges, textures, and shapes, enabling AI to identify objects within images with remarkable accuracy. Recurrent neural networks, RNNs, on the other hand, are tailored for sequential data such as language and time series. Their architecture allows them to remember previous inputs, capturing context and dependencies over time. This makes RNNs valuable for tasks like speech recognition and language translation. Yet traditional RNNs face challenges with long-term dependencies, which led to innovations like long short-term memory, LSTM networks, and gated recurrent units, GRUs. These variants improve the AI's ability to retain relevant information over longer sequences, enhancing performance in complex language tasks. In recent years, transformer models have emerged as a groundbreaking architecture, especially in natural language processing. Unlike RNNs, transformers process all parts of a sequence simultaneously, using attention mechanisms to weigh the importance of each element. This parallelism accelerates training and enables the model to capture nuanced relationships within data. The development of transformer models has led to powerful language models such as GPT, BERT, and others that can generate human-like text, translate languages, summarize content, and answer questions with impressive fluency and coherence. These models demonstrate AI's leap from simple pattern recognition to sophisticated understanding and generation of language. Training these models requires massive computational resources. Large datasets, sometimes comprising billions of words or images, feed into networks with millions or billions of parameters. The training process can take days or weeks on specialized hardware clusters. This scale of computation enables AI to achieve remarkable generalization and versatility. However, with great power comes great responsibility. The scale of data and computation means that energy consumption and environmental impact have become concerns. Researchers are actively exploring ways to make AI training more efficient and sustainable without sacrificing performance. Beyond models and data, AI systems rely on frameworks and tools that make development accessible and scalable. Libraries like TensorFlow, PyTorch, and Keras provide building blocks for creating, training, and deploying models. These tools abstract complex mathematical operations, allowing developers to focus on designing and experimenting with architectures. The ecosystem surrounding AI continues to expand, with cloud platforms offering AI as a service, enabling businesses and individuals to leverage powerful AI capabilities without owning hardware. This democratization accelerates innovation, but also raises questions about data privacy, security, and equitable access. Understanding AI also involves recognizing the feedback loops between AI and humans. AI systems learn from human-generated data, which reflects human behaviors, choices, and biases. When AI influences decisions, in hiring, lending, or policing, it can perpetuate or amplify existing societal issues. Ethical AI development demands vigilance, transparency, and inclusiveness to mitigate harm and promote fairness. Another intriguing dimension of AI is its capacity for creativity. Traditionally seen as a uniquely human trait, creativity in AI manifests through generative models that compose music, paint images, write poetry, and design products. These models learn patterns from vast artistic datasets and synthesize novel content, challenging notions of originality and authorship. Generative adversarial networks, GANs, are a key innovation here. GANs pit two neural networks against each other. One generates content, and the other evaluates its authenticity. Through this adversarial process, the generator improves, producing outputs increasingly indistinguishable from real examples. GANs have been used to create realistic images, deepfake videos, and new artistic styles. While AI's creative feats are impressive, they provoke philosophical questions about the nature of art and intelligence. Can machines truly create, or are they simply remixing existing data? How do we value AI-generated works compared to human creations? These questions remain open, reflecting the evolving relationship between humans and machines. In summary, the workings of AI are a tapestry woven from data, models, computation, and human insight. This intricate interplay enables machines to learn, reason, and create, expanding the horizons of what technology can achieve. As we peer deeper into this tapestry, we see not just the mechanics of AI, but the reflection of human curiosity, ingenuity, and the quest for understanding. Artificial intelligence is often described as the ability of machines to mimic human intelligence, but this analogy only scratches the surface. To understand AI's true nature, we must explore how it perceives the world, how it senses, interprets, and interacts with information much like humans do, but in uniquely digital ways. One crucial area where AI demonstrates remarkable capability is computer vision. This field focuses on enabling machines to see and interpret visual data, images, and videos in a way that mimics human sight. While our eyes and brains work seamlessly to understand the world visually, AI uses mathematical models and algorithms to achieve a similar outcome. The process begins with image acquisition, where digital sensors capture visual input. These images are then converted into arrays of numerical values representing pixels. AI models analyze these pixel patterns, searching for features such as edges, textures, colors, and shapes. The goal is to identify meaningful objects, people, or scenes within the image. Early computer vision techniques relied heavily on handcrafted features, where engineers designed specific filters or detectors to recognize particular patterns. These methods were limited in their flexibility and struggled with complex images or varying conditions such as lighting and angle. The advent of deep learning, particularly convolutional neural networks, CNNs, revolutionized computer vision. CNNs automatically learn hierarchical features from data, enabling AI to recognize intricate patterns with high accuracy. For example, CNNs can differentiate between a cat and a dog, identify faces in a crowd, or even detect tumors in medical scans. Beyond static images, AI extends its vision to video analysis. By processing sequences of frames, AI can track objects over time, detect activities, and even predict future movements. This capability powers applications like surveillance, autonomous vehicles, and gesture recognition. Complementing vision, AI's ability to understand sound, known as speech recognition or audio processing, unlocks a wealth of possibilities. Machines analyze waveforms, frequencies, and temporal patterns in audio signals to transcribe speech, detect emotions, or identify speakers. Speech recognition technology has progressed from simple command-based systems to complex conversational agents capable of natural dialogue. Virtual assistants like Siri, Alexa, and Google Assistant use sophisticated models trained on vast data sets of spoken language to understand accents, dialects, and contextual nuances. Another fascinating dimension is natural language understanding, where AI interprets the meaning, intent, and sentiment behind text or speech. This requires models that grasp syntax, semantics, and pragmatics, the layers of language that convey not just words but ideas and emotions. AI systems can now analyze large volumes of text for sentiment analysis, topic detection, and summarization. These tools assist businesses in understanding customer feedback, monitoring social media, and extracting insights from documents. Furthermore, AI's interaction with the physical world is enhanced by robotics, where intelligent algorithms control machines to perform tasks. Robots combine perception, reasoning, and actuation to navigate environments, manipulate objects, and collaborate. With humans, robotics integrates AI with sensors, motors, and control systems. Autonomous drones survey landscapes, robotic arms assemble products, and assistive robots help the elderly. Each robotic system requires AI to process sensory data, plan actions, and adapt to dynamic surroundings. The synergy between AI and robotics opens possibilities for automation in industries, disaster response, and exploration, extending human reach into environments that are hazardous or inaccessible. To enable such sophisticated interaction, AI relies on knowledge representation and reasoning. This involves encoding facts, rules, and relationships in formats that machines can manipulate logically. Knowledge graphs, ontologies, and symbolic reasoning allow AI to make inferences, answer questions, and solve problems. For example, expert systems in medicine use encoded knowledge to support diagnosis by matching symptoms to diseases and suggesting treatments. These systems complement data-driven models by providing explicit, interpretable reasoning. However, symbolic AI has limitations in handling uncertainty, ambiguity, and learning from raw data, which is where statistical and neural approaches excel. Modern AI often combines symbolic and sub-symbolic methods to leverage the strengths of both. Another critical concept in AI is generalization, the ability to apply learned knowledge to new, unseen situations. Without generalization, AI models would be brittle, failing whenever encountering data outside their training set. Achieving robust generalization involves careful model design, regularization techniques to prevent overfitting, and diverse training data. It also inspires research into lifelong learning, where AI continuously acquires and updates knowledge over time, much like humans do. Transfer learning is a related technique where knowledge gained from one task helps improve performance on another. For example, a model trained on millions of images can be fine-tuned to identify specific objects with much less data, accelerating development. Despite these advances, AI still faces challenges in common-sense reasoning, understanding everyday knowledge and intuitive facts that humans take for granted. AI may struggle with ambiguity, metaphor, or abstract concepts that require contextual awareness. Progress toward bridging this gap involves integrating language models with world knowledge databases and enhancing multimodal understanding, combining vision, language, and other sensory data to form richer representations. In all these endeavors, explainability remains a pressing concern. As AI systems grow more complex and embedded in critical applications, understanding how and why decisions are made becomes vital for trust, accountability, and ethical use. Techniques such as feature importance analysis, model distillation, and visualization tools help illuminate AI's inner workings, making them more transparent to developers and users alike. As we delve deeper into how AI perceives and interacts with the world, we recognize a remarkable convergence of mathematics, engineering, and cognitive science. AI's ability to see, hear, understand, and act embodies a profound synthesis of human knowledge and machine efficiency. This synthesis promises to transform every aspect of our lives, unlocking innovations in healthcare, education, transportation, and creativity. Yet it also calls us to reflect on the nature of intelligence itself, what it means to perceive, to understand, and to be aware. Artificial intelligence's true power lies not only in perception and understanding, but also in decision-making, the ability to choose actions based on information, goals, and constraints. This capacity mirrors human judgment, yet operates within the digital realm through algorithms and optimization. At its core, AI decision-making involves evaluating options and selecting the best course of action according to defined criteria. This process is essential in applications ranging from recommendation systems and autonomous vehicles to financial trading and medical diagnosis. One of the foundational approaches in AI decision-making is search and optimization. Search algorithms explore possible choices or paths to find optimal or satisfactory solutions. For example, in chess-playing AI, the system evaluates millions of potential moves ahead to decide the best next step, balancing offensive and defensive strategies. Optimization extends this idea by mathematically formulating problems where AI seeks to maximize or minimize objective functions. These could be profits, efficiency, accuracy, or other measurable goals. Techniques such as linear programming, genetic algorithms, and simulated annealing help AI navigate complex problem spaces efficiently. In uncertain and dynamic environments, AI must balance exploration and exploitation, the dilemma between trying new actions to gain knowledge and using known actions that yield high rewards. Reinforcement learning, RL, addresses this challenge by training AI agents through trial and error, receiving feedback in the form of rewards or penalties. Reinforcement learning mimics how living beings learn from interaction with their environment. Agents perceive states, take actions, and receive feedback, gradually improving their policies to maximize cumulative rewards. This approach powers successes in games like Go and complex robotic control. The interplay between reinforcement learning and deep learning, known as deep reinforcement learning, combines the strengths of both. Deep neural networks provide powerful function approximation, enabling agents to handle high-dimensional sensory inputs like images and sound, while RL algorithms drive policy improvement. Deep reinforcement learning has achieved breakthroughs beyond games, including autonomous driving, robotic manipulation, and energy management. It exemplifies AI's potential for adaptive, goal-directed behavior in complex real-world settings. Another dimension of AI decision-making is probabilistic reasoning, where uncertainty is explicitly modeled. Bayesian networks and Markov decision processes, MDPs, provide frameworks to represent and infer probabilities, enabling AI to make informed decisions even with incomplete or noisy data. Probabilistic models allow AI to quantify risks, update beliefs with new evidence, and plan under uncertainty. This capability is crucial in domains such as medical diagnosis, weather forecasting, and natural language understanding. Planning algorithms extend decision-making by generating sequences of actions to achieve long-term objectives. Classical planning methods involve searching through possible action sequences, considering preconditions and effects. In contrast, hierarchical planning breaks down complex goals into manageable sub-goals, mirroring human problem-solving strategies. The integration of planning with learning enhances AI's versatility, allowing systems to adapt plans based on experience and changing conditions. This fusion supports applications in robotics, logistics, and intelligent assistance. Ethical decision-making in AI introduces profound questions about values, fairness, and responsibility. As AI systems influence critical areas like healthcare, justice, and finance, ensuring decisions align with societal norms and human rights becomes paramount. Techniques for embedding ethics into AI include value alignment, where systems are designed to act according to human values, fairness, aware algorithms that mitigate bias, and accountability frameworks to trace and justify decisions. Transparency and interpretability also play vital roles. Stakeholders must understand how AI reaches conclusions, especially in high-stakes scenarios. Explainable AI, XAI, aims to create models and tools that reveal decision processes without compromising performance. Moreover, human-in-the-loop approaches involve humans guiding, supervising, or intervening in AI decision-making, combining the strengths of both. This collaboration fosters trust, improves outcomes, and addresses limitations of purely automated systems. Decision-making in AI is not confined to isolated systems, but often unfolds in multi-agent settings, where multiple intelligent entities interact, cooperate, or compete. Game theory provides mathematical models to analyze such interactions, exploring strategies and equilibria. Multi-agent systems enable applications like distributed sensing, collaborative robotics, and autonomous traffic management. They require AI to negotiate, communicate, and adapt to others' behaviors, reflecting complex social dynamics. As AI decision-making evolves, it increasingly embraces context awareness, understanding situational factors, preferences, and goals to tailor actions appropriately. Contextual AI enhances personalization, responsiveness, and relevance. In sum, AI decision-making is a rich tapestry woven from search, optimization, learning, reasoning, ethics, and social interaction. It transforms raw perception and knowledge to purposeful action, opening new frontiers in technology and human experience. Artificial intelligence, at its essence, is a reflection of humanity's quest to understand and recreate intelligence itself. As we have seen, AI perceives, understands, and decides. But another key dimension of intelligence is communication, the ability to exchange information, share meaning, and collaborate. AI's capacity to communicate bridges machines and humans, transforming isolated data into shared knowledge and cooperative action. Natural language processing, or NLP, is the AI discipline dedicated to understanding and generating human language. Language is complex, layered with syntax, semantics, pragmatics, and cultural nuance. Teaching machines to comprehend this richness requires sophisticated models and vast amounts of linguistic data. Early NLP efforts focused on rule-based systems and simple statistical methods. These approaches worked well for limited domains, but struggled with ambiguity, idioms, and the fluid nature of human language. The breakthrough came with machine learning techniques, especially deep learning, enabling models to learn language patterns from vast corpora. Modern language models such as transformers have revolutionized NLP. These architectures capture long-range dependencies in text, enabling machines to generate coherent and contextually relevant responses. They can translate languages, summarize texts, answer questions, and even create poetry or stories. The implications of such AI language understanding are profound. Virtual assistants can hold natural conversations, chatbots provide customer support around the clock, and tools assist in content creation and education. Language models democratize knowledge access and foster global connectivity. Yet language AI also faces challenges. Understanding intent, sarcasm, emotion, and cultural references remains difficult. Models can inadvertently reproduce biases present in training data, raising concerns about fairness and misinformation. Dialogue systems strive to create meaningful interactions that go beyond scripted responses. They aim to remember context, manage topics, and exhibit empathy. This human-like communication is essential for applications in mental health support, education, and personal companionship. Multimodal communication, integrating language with vision, sound, and gesture, further enriches AI's interactive abilities. For example, an AI that can interpret spoken words while recognizing facial expressions and body language can respond more naturally and appropriately. Beyond verbal communication, AI systems increasingly communicate with each other. Interconnected. AI agents share data, coordinate actions, and learn collectively. This networked intelligence enhances efficiency and innovation in smart cities, industrial automation, and scientific research. Secure and reliable communication protocols ensure that AI networks operate safely, protecting against cyber threats and ensuring data privacy. Trustworthy communication infrastructure is critical as AI becomes more embedded in critical infrastructure and daily life. The fusion of communication with cognition transforms AI from isolated calculators into interactive partners capable of understanding context, emotions, and intentions. This evolution challenges us to rethink what it means to converse, collaborate, and connect with machines. Moreover, AI's ability to generate creative content is an exciting frontier. From composing music to designing art and writing literature, AI explores the realm of imagination. These creative systems learn styles, experiment with forms, and collaborate with human artists, expanding the boundaries of creativity. Creativity in AI raises questions about originality, authorship, and value. While machines generate novel combinations of existing knowledge, human insight and emotional depth remain irreplaceable. The partnership between human and machine creativity opens new possibilities for expression and innovation. As AI continues to master perception, decision, and communication, it shapes a future where intelligent systems become integral companions in our personal and professional lives. Understanding how AI communicates and creates helps us embrace these changes with insight and responsibility. In exploring the landscape of artificial intelligence, it becomes clear that data is its lifeblood, the foundation upon which all AI systems are built and refined. Without data, AI would have no context, no learning material, and no means to adapt or improve. Understanding the role and nature of data in AI illuminates how machines transform raw information into meaningful intelligence. Data comes in many forms: numbers, text, images, audio, video, and sensor readings. Each form holds a unique structure and complexity, requiring tailored processing techniques. For AI, the process begins with data collection, gathering vast and diverse examples that represent the world as accurately as possible. The quality and quantity of data directly influence AI's performance. Large data sets enable models to learn subtle patterns, generalize better, and avoid overfitting. Conversely, poor quality or biased data can lead to inaccurate predictions, unfair outcomes, or unintended consequences. Data pre-processing is a critical step that cleans, organizes, and transforms raw data into formats suitable for machine learning. This includes handling missing values, normalizing ranges, encoding categorical variables, and removing noise or outliers. Feature engineering, the art of selecting and crafting relevant attributes from data, helps models focus on the most informative aspects. Good features improve learning efficiency and accuracy, often reflecting domain knowledge and human insight. In recent years, end-to-end deep learning has reduced the need for manual feature engineering by automatically extracting hierarchical features from raw data. This shift allows AI to discover intricate representations, especially in unstructured data like images and audio. Labeling or annotating data is another essential component, especially for supervised learning. Human annotators provide ground truth by categorizing images, transcribing speech, or tagging sentiments in text. This supervised guidance steers AI models toward desired outputs. However, data labeling can be expensive, time-consuming, and prone to errors. Techniques like semi-supervised learning, active learning, and self-supervised learning help alleviate these challenges by leveraging unlabeled data or focusing annotation efforts strategically. Data augmentation artificially expands datasets by generating variations through transformations such as rotation, cropping, or noise addition. This enhances model robustness and generalization, particularly in fields like computer vision. Moreover, synthetic data, created through simulations or generative models, supplements real data when availability is limited. Synthetic datasets can help train AI in rare or hazardous scenarios, such as autonomous driving in extreme weather or medical diagnostics for uncommon diseases. Data privacy and security have become paramount concerns as AI relies heavily on personal and sensitive information. Regulations like GDPR and CCPA impose strict requirements on data collection, usage, and protection. Techniques such as differential privacy, federated learning, and secure multi-party computation enable AI to learn from data while preserving user confidentiality. Federated learning, for instance, allows models to be trained across distributed devices without sharing raw data, safeguarding privacy. Bias in data is a significant ethical challenge. Historical, social, or sampling biases can be encoded into datasets, leading AI to perpetuate unfair stereotypes or discriminatory practices. Identifying and mitigating bias requires vigilance, diverse datasets, and fairness-aware algorithms. Data governance, policies, standards, and accountability ensures responsible data management throughout AI development and deployment. Transparency about data sources, quality, and limitations fosters trust among users and stakeholders. As data fuels AI's ability to recognize patterns, make predictions, and generate insights, it also shapes the boundaries of what AI can understand and achieve. Continuous efforts to improve data practices drive advancements in accuracy, fairness, and applicability. In this interplay between data and intelligence, AI mirrors human learning, absorbing experience, refining knowledge, and adapting to new information. Yet, unlike humans, AI's capacity to process and analyze data at scale unlocks unprecedented potential for discovery and innovation. Ultimately, the relationship between data and AI is a dynamic, evolving partnership, one that defines the present and future of intelligent technology. As artificial intelligence grows more capable, the architectures that underpin its learning processes become increasingly sophisticated. One of the most influential innovations in recent years is the neural network, a computational framework inspired by the biological networks of neurons in the human brain. To understand how AI learns and generalizes, it is essential to delve into the structure and function of these artificial neural networks. At their simplest, neural networks consist of layers of interconnected nodes, or neurons, each performing mathematical operation on its inputs to produce an output. These networks are composed of an input layer, one or more hidden layers, and an output layer. Data passes through these layers, undergoing transformations that extract features and enable pattern recognition. The power of neural networks lies in their ability to approximate complex functions, mapping inputs to outputs in highly nonlinear ways. Each connection between neurons carries a weight, which determines the strength of influence from one neuron to another. By adjusting these weights through a process called training, the network learns to perform specific tasks such as image classification, language translation, or speech recognition. Training a neural network involves feeding it large amounts of labeled data and using an optimization algorithm to minimize the error between the predicted outputs and the true labels. The most common optimization method is gradient descent, which iteratively updates weights in the direction that reduces error. Backpropagation is the algorithm that makes gradient descent feasible for neural networks. It computes how much each weight contributes to the final error, allowing the system to update them efficiently. This iterative learning process gradually tunes the network to recognize patterns and make accurate predictions. Deeper networks with many hidden layers, called deep neural networks, have revolutionized AI by enabling the extraction of hierarchical features. Early layers detect simple patterns like edges in images, while deeper layers combine these features into more abstract concepts such as shapes or objects. This hierarchical learning mimics aspects of human perception, where the brain processes sensory inputs in stages, building from raw data to meaningful understanding. The success of deep learning across vision, speech, and language domains attests to the power of these architectures. Convolutional neural networks, CNNs, specialize in analyzing spatial data, particularly images. They use convolutional layers to scan input data with filters that detect local features, reducing the number of parameters and improving efficiency. CNNs excel at tasks like object detection, facial recognition, and medical imaging. Recurrent neural networks, RNNs, and their variants such as long short-term memory, LSTM networks, are designed to process sequential data, capturing dependencies over time. These models are particularly suited for language modeling, speech, synthesis, and time series prediction. Transformer architectures, introduced more recently, have reshaped natural language processing by enabling parallel processing of sequences and modeling long-range dependencies more effectively than RNNs. This innovation underpins modern language models that generate coherent, context-aware text. Despite their successes, neural networks require vast amounts of data and computational resources. Training deep models can be time-consuming and energy-intensive, prompting research into more efficient architectures and learning methods. Furthermore, neural networks are often considered black boxes, making it difficult to interpret their decision-making processes. This opacity raises concerns about reliability, fairness, and accountability in critical applications. Explainable AI seeks to unravel these black boxes by developing tools and methods that provide insights into how networks reach their conclusions. Techniques like saliency maps, attention visualization, and surrogate models help stakeholders understand and trust AI systems. The flexibility of neural networks also allows for transfer learning, where a model trained on one task is fine-tuned for another, reducing the need for large data sets and accelerating development. This approach has democratized AI, enabling broader access to powerful models. As neural networks evolve, hybrid models that combine symbolic reasoning with deep learning emerge, aiming to merge the strengths of rule-based and data-driven AI. These efforts seek to build systems capable of both learning from data and reasoning with knowledge, expanding the horizons of artificial intelligence. In essence, neural networks embody the fusion of inspiration from biology, mathematical rigor, and computational power. They form the backbone of modern AI, translating raw data into meaningful understanding and intelligent behavior. Beyond the architecture of neural networks and the mechanisms of learning, the journey of artificial intelligence also involves how machines perceive the world around them. Perception, the ability to interpret sensory data, is fundamental to intelligence. For AI, perception translates into processing raw inputs from cameras, microphones, sensors, and other devices into structured information that can be understood and acted upon. Computer vision is the field dedicated to enabling machines to interpret images and videos. It bridges pixels and patterns, transforming visual data into meaningful insights. Early computer vision techniques relied on handcrafted features such as edges, corners, and textures. These methods, while effective in controlled environments, struggled with variability in lighting, viewpoint, and occlusions. The advent of deep learning transformed computer vision, by allowing AI to learn features directly from raw images. Convolutional neural networks, CNNs, as previously mentioned, scan images with multiple layers of filters to detect increasingly complex features, from lines and shapes to faces and objects. This capability enables a wide range of applications. Autonomous vehicles recognize pedestrians and obstacles. Security systems identify faces for authentication. Medical imaging tools detect tumors and anomalies, and photo apps tag people and enhance images automatically. Object detection goes a step further by not only identifying objects in an image, but also locating them precisely with bounding boxes. Semantic segmentation divides images into regions corresponding to different classes, enabling detailed scene understanding. Beyond static images, video analysis adds the dimension of time, allowing AI to track movements, recognize actions, and predict future events. This temporal understanding is crucial for applications in surveillance, sports analytics, and robotics. Speech recognition is another critical perception task, transforming spoken language into text. It requires processing audio signals, identifying phonemes, and mapping them to words, all while handling variations in accents, background noise, and speech patterns. Advancements in deep learning have dramatically improved speech recognition, accuracy, powering virtual assistants, automated transcription, and real-time translation services. These systems enable hands-free interaction and accessibility for people with disabilities. Auditory perception extends to understanding sounds. Beyond speech, AI can classify environmental sounds, detect anomalies in machinery, and even recognize emotions in voice tone. This broadens AI's ability to monitor environments and respond empathetically. Sensor fusion integrates data from multiple sources, visual, auditory, tactile, and more, to build a comprehensive representation of the surroundings. Autonomous vehicles, for example, combine cameras, radar, lidar, and GPS to navigate safely. Perception in AI is not merely about data acquisition, but about interpreting context and making sense of complexity. This involves filtering noise, recognizing patterns, and adapting to dynamic environments. Challenges in perception include dealing with incomplete, ambiguous, or contradictory data. AI systems must generalize from limited examples and handle unexpected situations gracefully. Robustness and reliability in perception are vital for safety-critical applications like healthcare and transportation. Perception also underpins human-AI interaction. Recognizing facial expressions, gestures, and emotions enables machines to respond naturally and appropriately. This emotional intelligence enhances user experience and broadens AI's social role. As AI's perceptual capabilities advance, the line between virtual and physical worlds blurs. Augmented reality overlays digital information onto real environments, while virtual reality immerses users in artificial spaces. AI powers these experiences by understanding and adapting to user actions. Ultimately, perception transforms raw, sensory inputs into actionable knowledge, enabling AI to perceive, understand, and engage with the world in ways that echo human senses. This capacity forms the foundation for intelligent behavior and meaningful interaction. With perception and learning as pillars of artificial intelligence, the question naturally arises: how do AI systems use what they learn to make decisions? Decision-making is the process by which AI evaluates options, weighs consequences, and selects actions to achieve specific goals. This ability to act purposefully based on input data and learned knowledge defines intelligence in its most practical form. At the heart of AI decision-making lies the concept of algorithms, precise sets of rules or instructions that guide how tasks are performed. Traditional algorithms operate deterministically, following clear-cut steps to produce predictable outcomes. However, real-world problems are often uncertain, complex, and dynamic, requiring more flexible and adaptive approaches. Enter machine learning models and probabilistic reasoning. These frameworks enable AI to handle ambiguity and make decisions under uncertainty by estimating the likelihood of various outcomes. Probabilistic models represent knowledge as probabilities, updating beliefs as new information arrives. Bayesian inference, for instance, provides a mathematical foundation for updating probabilities based on observed evidence. This approach allows AI to combine prior knowledge with new data, refining its understanding and guiding decisions accordingly. Reinforcement learning, a powerful branch of AI, models decision-making as a trial-and-error process. An agent interacts with an environment, takes actions, and receives feedback in the form of rewards or penalties. Through this feedback loop, the agent learns policies, mappings from states to actions that maximize cumulative reward over time. This paradigm mimics natural learning processes observed in animals and humans, where experiences shape behavior by reinforcing beneficial actions. Reinforcement learning has enabled breakthroughs in robotics, game playing, and autonomous systems. In practice, reinforcement learning agents perceive their environment, evaluate possible moves, anticipate consequences, and adapt strategies dynamically. Challenges include balancing exploration of new options with exploitation of known rewards, handling delayed feedback, and scaling to complex environments. Decision trees and random forests represent another class of models used for decision-making. These structures resemble flowcharts, where each node poses a question about input features, guiding the path to a final decision. They are intuitive, interpretable, and effective for classification and regression tasks. Support vector machines and logistic regression models provide alternative decision boundaries in high-dimensional spaces, separating data points into categories with optimized margins or probabilities. Optimization techniques, such as linear programming and constraint satisfaction, further empower AI to select the best options under given limitations. These methods find applications in logistics, scheduling, finance, and resource management. In many AI systems, decision-making is tightly integrated with perception and learning. For example, an autonomous vehicle perceives its surroundings, predicts other agents' behavior, plans safe trajectories, and executes maneuvers, all in real time. Ethical considerations surface prominently in AI decision-making. When algorithms influence life-changing outcomes, from medical diagnoses to criminal justice, fairness, transparency, and accountability become paramount. Ensuring that AI decisions do not reinforce biases or harm vulnerable groups demands rigorous oversight. Explainability helps stakeholders understand why an AI system made a particular decision, fostering trust and enabling human review. Methods, such as rule extraction, feature importance analysis, and counterfactual explanations, contribute to this goal. As AI continues to permeate daily life, decision-making processes grow more complex and interconnected. Multi-agent systems, where numerous AI entities interact, negotiate, and collaborate, resemble social dynamics and collective intelligence. Game theory provides a framework for analyzing strategic interactions among rational agents, informing AI design in competitive and cooperative scenarios. Applications range from economic markets to cybersecurity and automated negotiation. Hybrid systems that combine symbolic reasoning with machine learning enable AI to incorporate explicit knowledge, rules, and logic alongside learned patterns. This fusion enhances decision quality, interpretability, and adaptability. Ultimately, decision-making embodies AI's capacity to transform understanding into action. It reflects intelligence's essence, the purposeful pursuit of goals through informed choices guided by data, experience, and reasoning. As artificial intelligence systems grow more advanced in learning, perceiving, and decision-making, a critical component comes into focus: natural language processing, or NLP. This field enables machines to understand, interpret, generate, and respond to human language, bridging the gap between artificial systems and human communication. Language is uniquely complex, filled with nuances, ambiguity, cultural context, idioms, and evolving meanings. For AI to engage meaningfully with humans, it must navigate syntax, semantics, pragmatics, and discourse, layers of meaning that go far beyond simple word recognition. Early attempts at language understanding relied on rule-based systems and handcrafted grammars, which struggled with the vast diversity and unpredictability of natural language. The rise of machine learning shifted the paradigm toward data-driven models that learn language patterns from large text corpora. Statistical models analyzed word frequencies, co-occurrences, and contextual probabilities, laying groundwork for more flexible understanding. Techniques like n-grams captured sequences of words, providing basic predictive capabilities. The advent of neural networks brought dramatic improvements. Recurrent neural networks, RNNs, and long short-term memory, LSTM units, enabled models to process sequences with memory, capturing dependencies across sentences and paragraphs. More recently, transformer architectures revolutionized NLP by leveraging attention mechanisms, which allow models to weigh the importance of different words and phrases dynamically. Transformers process language in parallel, enabling faster and more effective training on massive datasets. These advances gave birth to large-scale language models capable of generating coherent text, answering questions, summarizing documents, translating languages, and engaging in conversations. Such models simulate understanding by predicting the most probable next word or phrase given the context. Despite these breakthroughs, challenges remain. Language understanding involves not only syntax, but also semantics, grasping meaning and pragmatics, recognizing intent and context. Sarcasm, humor, metaphor, and cultural references often confound AI. Furthermore, language is inherently social and evolving, reflecting human experience and creativity. AI models require continual updates and contextual learning to stay relevant and sensitive. Multilingual NLP expands AI's reach globally, addressing diverse languages with different structures and scripts. Transfer learning and multilingual training help models generalize across languages, promoting inclusivity. Dialogue systems and chatbots demonstrate AI's ability to engage interactively, providing assistance, customer support, and companionship. These systems must balance responsiveness, relevance, and naturalness to foster meaningful interactions. Natural language generation powers creative applications, including story writing, poetry, and music composition, pushing the boundaries of machine creativity. This raises profound questions about authorship, originality, and human-machine collaboration. Ethical considerations in NLP include mitigating biases encoded in training data, preventing misuse for misinformation, and respecting privacy in language data. Responsible AI development emphasizes transparency, fairness, and human oversight. Language interfaces herald a future where AI is accessible and intuitive, dissolving barriers between humans and machines. Voice assistants, real-time translation, and accessible communication tools exemplify this transformation. In essence, natural language processing breathes communicative life into artificial intelligence. It enables machines not just to process data, but to participate in human dialogue, understand intent, and express ideas, foundations of intelligence deeply woven into the fabric of human society. The evolution of artificial intelligence has led to a remarkable convergence of technologies that bring machines closer to human-like cognition. One such frontier is the integration of reasoning and knowledge representation, mechanisms that allow AI to store, organize, and apply information logically, bridging raw data and actionable insight. Knowledge representation involves encoding facts, concepts, relationships, and rules in a form that machines can process. Unlike the pattern-based learning of neural networks, knowledge representation emphasizes symbolic structures, logical inference, and explicit understanding. Ontologies, semantic networks, and knowledge graphs are common frameworks used to represent complex, interrelated information. These structures capture entities, attributes, and relationships, enabling machines to reason about the world with clarity and precision. For example, a knowledge graph might encode that Paris is the capital of France. France is a country in Europe, and Europe is a continent, allowing AI to infer new facts, answer questions, and navigate concepts logically. Logic-based systems use formal rules and inference engines to derive conclusions, check consistency, and validate information. They support deductive reasoning, where truths follow necessarily from premises, and abductive reasoning, where best explanations are hypothesized from observations. Such capabilities are vital in domains requiring transparency, explainability, and rigorous decision-making, medical diagnosis, legal reasoning, and scientific discovery. Hybrid AI approaches combine symbolic reasoning with machine learning, seeking to harness the strengths of both. Symbolic methods provide interpretability and structure. Machine learning offers flexibility and scalability. This synergy addresses some limitations of purely data-driven AI, such as brittleness in unfamiliar scenarios and lack of common-sense knowledge. Common sense itself is a profound challenge. It encompasses everyday knowledge, intuitions, and expectations humans take for granted but find hard to formalize. Efforts in AI aim to build repositories of common-sense facts and rules, enabling machines to reason about ordinary situations and avoid absurd conclusions. Automated theorem proving and knowledge extraction from text contribute to expanding AI's knowledge bases, enriching its reasoning abilities. Cognitive architectures aspire to model human thought processes, integrating perception, learning, memory, reasoning, and planning in unified frameworks. These architectures strive for general intelligence, capable of adapting across diverse tasks. Moreover, reasoning enables AI to explain its decisions, providing insights into its thought process. Explainable AI is crucial for building trust and facilitating collaboration between humans and machines. In complex systems, reasoning supports metacognition, AI's ability to reflect on its own knowledge and performance, adjust strategies, and learn from mistakes. As AI matures, the interplay between knowledge, learning, and reasoning becomes more sophisticated, resembling the rich cognitive abilities of humans. This integration empowers AI not only to recognize patterns but to understand meanings, draw logical connections, and apply knowledge creatively and flexibly. It is a crucial step toward building truly intelligent systems that can assist, augment, and collaborate with humans in ever more meaningful ways. In the journey toward intelligent machines, the role of perception cannot be overstated. Among various sensory modalities, vision stands out as a gateway for AI to interpret and interact with the physical world. Computer vision is the field dedicated to enabling machines to see, analyze, and understand visual information from images and videos. Human vision is extraordinarily complex, effortlessly recognizing objects, faces, scenes, and actions within milliseconds. Replicating this feat demands algorithms capable of processing vast arrays of pixels, extracting meaningful patterns, and interpreting spatial relationships. Early computer vision methods relied on handcrafted features, edges, corners, textures, designed by experts to capture salient image properties. These features fed into classifiers to identify objects or detect patterns. The rise of deep learning revolutionized computer vision by allowing AI to learn hierarchical features automatically from raw pixels. Convolutional neural networks, CNNs, became the cornerstone of this revolution. CNNs mimic the visual cortex's structure, applying filters across images to detect edges, shapes, and textures, progressively building complex representations. With sufficient data and computational power, CNNs achieve remarkable accuracy in tasks such as image classification, object detection, and facial recognition. Beyond static images, AI interprets dynamic scenes through video analysis, recognizing actions, gestures, and events over time. This capability enables applications like surveillance, autonomous driving, and human-computer interaction. Semantic segmentation breaks images into meaningful regions, assigning labels to each pixel, allowing detailed scene understanding. For example, distinguishing roads, pedestrians, vehicles, and traffic signs in self-driving car systems. Depth, estimation, and 3D reconstruction extend vision into 3 dimensions, enabling spatial awareness and navigation. Stereo vision, lidar, and structured light are among sensing technologies used alongside AI algorithms to achieve this. Generative models in computer vision create new images, enhancing creativity and design. Techniques such as generative adversarial networks, GANs, produce realistic images, style transfer, and image inpainting. Vision applications permeate healthcare through medical imaging analysis, detecting tumors, abnormalities, and assisting diagnostics with unprecedented precision. Ethical and privacy concerns arise as AI vision systems monitor public spaces and personal environments. Balancing technological benefits with respect for individual rights demands careful regulation and transparency. In essence, computer vision empowers machines with eyes, transforming pixels into perception, knowledge, and action. It bridges the digital and physical worlds, enabling AI to understand and navigate the visual tapestry of reality. Alongside vision, speech, and audio processing, open another essential channel for artificial intelligence to connect with the world. Speech recognition, synthesis, and understanding enable machines to comprehend spoken language, respond naturally, and engage in meaningful dialogues. Human speech is a rich, continuous signal, filled with variations in tone, pitch, speed, and emotion. Capturing its nuances requires sophisticated signal processing and modeling techniques. Early speech recognition systems used rule-based phonetic models and template matching, which struggled with variability across speakers and environments. The introduction of statistical models and hidden Markov models, HMMs, improved robustness by modeling speech as sequences of probabilistic states. More recently, deep learning architectures have transformed speech processing. Recurrent neural networks and attention-based models capture temporal dependencies and contextual cues, dramatically enhancing accuracy. Speech-to-text systems convert audio into written language, powering voice assistants, transcription services, and accessibility tools. Natural language understanding layers interpret intent and context, enabling commands, questions, and conversations. Conversely, text-to-speech synthesis recreates human-like voices, enabling machines to communicate verbally. Advances in neural vocoders and waveform generation produce voices that are expressive, natural, and customizable. Emotion recognition from speech adds depth to interactions, allowing AI to sense moods, stress, or sarcasm, fostering empathetic communication. Beyond speech, audio analysis encompasses music recognition, environmental sound classification, and acoustic event detection. These capabilities find use in media indexing, security, and smart home devices. Integrating speech and vision gives rise to multimodal AI systems that perceive and understand through multiple senses simultaneously, akin to human perception. This synergy enhances context awareness and interaction quality. Challenges in speech. AI include handling diverse languages, dialects, accents, and noisy environments. Ensuring inclusivity and fairness across populations remains an ongoing goal. Privacy concerns emerge as voice data often contains sensitive personal information. Secure handling and transparency are critical to maintaining trust. Ultimately, speech and audio processing open conversational pathways between humans and machines, making AI more accessible, intuitive, and responsive. This auditory dimension complements vision and cognition, enriching AI's engagement with the world. The dance of intelligence extends beyond perception into the realm of movement, decision-making, and interaction. In this evolving symphony, robotics emerges as the embodiment of artificial intelligence, giving it form, mobility, and presence in the physical world. A robot is more than a machine. It is an agent that senses, thinks, and acts. It interprets data from cameras, sensors, gyroscopes, and encoders, and transforms that understanding into action through motors, actuators, and control systems. AI is the invisible thread weaving cognition into this mechanical shell. At the heart of robotic intelligence lies the concept of autonomy, the ability to operate independently, navigate unpredictability, and adapt to dynamic surroundings. Robots must localize their position, map unfamiliar terrain, and plan paths through cluttered or changing environments. This requires a fusion of perception, probabilistic reasoning, and motion planning. Algorithms like simultaneous localization and mapping, SLAM, allow robots to build maps while determining their position within them, anchoring them in physical reality without predefined coordinates. Robotic arms, guided by vision and haptic feedback, perform delicate tasks such as assembling microelectronics, conducting surgical procedures, or sorting fragile produce. Their precision, consistency, and learning capabilities revolutionize manufacturing, logistics, and medicine. In service robotics, AI enables companionship, assistance, and care. Robots greet customers, support the elderly, and entertain children. They understand voices, recognize faces, and respond to gestures. Their intelligence is not just functional, it becomes relational. Humanoid robots attempt to replicate human movement and expression. Their gait, balance, and gestures are orchestrated by complex control systems that mimic biomechanics and motor learning. Each motion is a solution to constraints imposed by gravity, friction, and joint limitations. Swarm robotics explores collective intelligence, where many simple agents collaborate to solve complex problems. Inspired by ants, bees, and flocks, swarms distribute intelligence across the group, achieving robustness, scalability, and flexibility. Soft robotics explores non-traditional materials, flexible, compliant structures that move with gentle adaptability. These robots bend, stretch, and deform, interacting safely with humans and delicate objects. Ethical considerations emerge as robots enter daily life. Questions of accountability, agency, and emotional attachment surface when machines gain autonomy and presence. What does it mean to coexist with entities that mimic life yet remain fundamentally artificial? The integration of AI into robotics does not merely automate tasks, it breathes purpose into machines, allowing them to act in the world with intention, awareness, and adaptive intelligence. From self-driving cars navigating bustling cities to drones inspecting power lines or delivering medicine to remote villages, robotics extends the reach of intelligence into tangible, transformative impact. It is here that thought meets action, where algorithms touch reality. The boundary between digital and physical dissolves, giving rise to a new class of beings, not living but learning, not born but built, who move through the world in rhythm with the code that drives them. As artificial intelligence grows, it becomes deeply intertwined with the vast ocean of data generated daily by humans and machines alike. Data is the lifeblood of AI, the raw material from which intelligence is forged. Yet the scale and complexity of data in the modern world demand innovative strategies for collection, management, and interpretation. Data comes in countless forms, structured and unstructured, numerical and textual, images and audio, sensor, streams and transactional records. Harnessing this diversity requires powerful pipelines that ingest, clean, and organize data efficiently. Big data technologies enable storage and processing at unprecedented scale. Distributed systems like Hadoop and Spark divide massive datasets across networks of machines, enabling parallel analysis and swift computation. But quantity alone is not enough. Quality matters deeply. AI thrives on clean, accurate, and representative data. Bias, noise, and errors can propagate through models, amplifying inaccuracies and unfairness. Data labeling is crucial. Annotating raw data with meaningful tags, categories, or attributes that guide supervised learning. This human-in-the-loop process demands expertise and effort, often supported by crowdsourcing or automated tools. Feature engineering transforms raw data into informative signals, extracting meaningful features, from frequency patterns in audio to shapes in images or sentiment in text, allows models to focus on relevant aspects of the problem. Data privacy and security loom large as AI systems access sensitive information. Anonymization, encryption, and federated learning techniques protect personal data while enabling collaborative model training. Moreover, data lifecycle management ensures that datasets remain current, consistent, and compliant with regulations. AI systems also learn from continuous streams of data in real time, adapting to changes and new trends. Online learning and reinforcement learning techniques enable this dynamic evolution. The interplay between data and AI is cyclical. Better data produces stronger models, which in turn generate more refined predictions and insights, driving further data collection and decision-making. In essence, data is the mirror reflecting reality's complexity. AI's ability to perceive, reason, and act depends profoundly on how well it understands this reflection. Thus, the data ecosystem forms the foundation of AI's power, a vast, intricate web of information fueling the rise of intelligent machines. Behind the impressive capabilities of artificial intelligence lies a critical component often overlooked: the infrastructure and hardware powering these complex systems. The invisible engines of silicon and circuits provide the computational might required to transform abstract algorithms into tangible results. Early computers, with their limited speed and memory, constrained the scope of AI research. Today's breakthroughs owe much to advances in processing power, storage, and networking. Central processing units, CPUs, serve as the general purpose brains of computers, adept at handling diverse tasks. However, AI workloads, particularly deep learning, demand highly parallel computation, a realm where graphics processing units, GPUs, excel. GPUs, originally designed to render images and video, possess thousands of cores capable of performing many operations simultaneously. This parallelism accelerates matrix multiplications and convolutions at the heart of neural networks, drastically reducing training times. Tensor processing units, TPUs, and specialized AI accelerators take this further. Tailored specifically for machine learning, they optimize data flow, precision, and energy efficiency, enabling large-scale model training and deployment. Memory technologies also play a vital role. High bandwidth, low-latency memory architectures ensure data moves swiftly between processors and storage, minimizing bottlenecks. Cloud computing platforms democratize access to vast computational resources. By renting processing power and storage on demand, researchers and companies can experiment with colossal datasets and models without massive upfront investment. Edge computing pushes intelligence closer to data sources, smartphones, sensors, autonomous vehicles, reducing latency and preserving privacy by processing information locally. Distributed computing frameworks orchestrate computations across clusters of machines, coordinating data sharding, synchronization, and fault tolerance. Hardware design increasingly integrates AI capabilities directly into chips, creating neural processing units, NPUs, embedded in mobile devices and IoT gadgets. Energy efficiency emerges as a critical challenge. The environmental footprint of training and running AI models prompts innovations in low-power architectures, model compression, and algorithmic efficiency. Quantum computing promises to revolutionize AI hardware by leveraging quantum phenomena for exponential speedups in certain computations, though practical quantum AI remains a future frontier. Ultimately, the synergy between algorithms and hardware forms the backbone of AI's explosive growth. Powerful machines transform theoretical ideas into practical, scalable intelligence that shapes industries and everyday life. Without this foundation of silicon and code, AI would remain an intriguing concept rather than a transformative force. As artificial intelligence increasingly permeates every aspect of our lives, understanding the ethical dimensions and societal implications becomes paramount. Intelligence without wisdom risks unintended consequences, bias, and harm. AI systems are only as fair and just as the data and values that shape them. Biased training data can embed prejudice, leading to discrimination in hiring, lending, law, enforcement, and beyond. Unchecked algorithms may reinforce existing inequalities rather than alleviate them. Transparency and explainability of AI decisions are critical for trust. Black box models, while powerful, can be inscrutable, making it difficult to diagnose errors or understand reasoning. Efforts in interpretable AI seek to reveal how and why models reach conclusions, empowering accountability. Privacy concerns arise as AI processes vast amounts of personal information. Striking a balance between utility and confidentiality requires rigorous data governance, encryption, and user consent frameworks. The automation of tasks by AI threatens job displacement in some sectors while creating opportunities in others. Societies must prepare for workforce transitions, education reforms, and social safety nets. Moreover, AI-enabled surveillance raises questions about civil liberties and freedom. The use of facial recognition, behavioral prediction, and social scoring systems calls for careful regulation to protect human rights. Autonomous systems, especially in defense and transportation, pose risks of malfunction or misuse. Establishing ethical guidelines and international agreements is essential to prevent harm. Inclusive design practices ensure AI benefits diverse populations, avoiding technological colonialism and digital divides. Ultimately, the stewardship of AI technology demands collaboration across disciplines, scientists, ethicists, policymakers, and the public to guide development aligned with human values. AI offers profound potential to enhance well-being, creativity, and knowledge. Yet this promise is inseparable from responsibility. In recognizing both the power and peril of intelligence crafted by human hands, we embark on a collective journey toward a future where machines amplify our highest aspirations rather than our deepest fears. The story of artificial intelligence is ultimately a story of connection between human minds and machines, between data and insight, between possibility and reality. At its core, AI is a mirror reflecting our quest to understand intelligence itself. From the simplest rule-based systems to the most complex neural networks, AI embodies an ongoing experiment in replicating the mind's faculties. Pattern recognition, learning, reasoning, perception, and decision-making come alive through layers of code and silicon. This journey has been propelled by curiosity, creativity, and collaboration, uniting mathematicians, engineers, neuroscientists, philosophers, and dreamers. Each breakthrough unfolds new horizons, machines that translate languages instantly, detect diseases early, compose music, and explore distant planets. The boundaries of what is possible expand continually. Yet AI also invites reflection on what makes us uniquely human. Consciousness, empathy, morality, and meaning remain profound. Mysteries beyond current machines' reach. As we build smarter tools, we are challenged to deepen our understanding of intelligence, not merely as computation, but as lived experience. The partnership between humans and AI holds transformative potential for knowledge, health, art, and the environment. It also asks us to define new paradigms of collaboration, machines augmenting human creativity rather than replacing it, intelligence expanding through shared insight. In this dance of minds and machines, we glimpse a future where artificial intelligence serves as both a tool and a companion, a reflection and a catalyst for growth. The story continues, written in algorithms and dreams, a testament to humanity's enduring quest to know and to create. As we stand at the threshold of an era shaped by artificial intelligence, the horizon gleams with both promise and challenge. The path forward invites us to embrace not only technological innovation, but also mindful stewardship. AI will continue to evolve, becoming more intuitive, adaptive, and integrated into the fabric of daily life. It will enhance our abilities, solve complex problems, and unlock new realms of discovery. Yet this unfolding future depends on choices about ethics, inclusivity, transparency, and responsibility. It calls for a balance between ambition and caution, between progress and preservation. Education must adapt, empowering individuals, to understand and engage with AI thoughtfully. Governance frameworks need to be agile, global, and participatory. We must nurture a culture where technology serves humanity's highest ideals: justice, compassion, creativity, and wisdom. Artificial intelligence is not an endpoint but a journey, a mirror reflecting our collective intellect and imagination. It challenges us to rethink intelligence itself and to envision a world where human and machine intelligence intertwine harmoniously. In this evolving narrative, each one of us plays a role, whether as creators, users, critics, or caretakers. Together, we shape the future of intelligence, crafting a legacy that honors both the power of technology and the depth of our humanity. This is the story of artificial intelligence, not just how it works, but why it matters.